Thank you, Yuri. Thanks to the Foundation for the invitation and the support, and thanks to all of you for sticking around to the bitter end. So yes, I'll be talking about research on data privacy. What's the general sort of family of questions when we talk about privacy? We have all these data sets being collected with lots of interesting information about human behavior and human health and interactions. And the question is, how can we enable this data to be used for things we consider to be good and valuable, while protecting the privacy of the people whose data is in these data sets? So many of these data sets have what many would consider to be sensitive information about people. Okay, so to make sense of this, there's really two things that we need to make sense of. What is the kind of desirable uses we want to support? So you may think of things from, academic research, informing government policy, identifying subjects for potential drug trial, searching for potential bad actors, and so on. And it's good to kind of keep in mind some of these possibilities, because the kinds of things, the technical solutions, the mathematics, will depend on, in a more abstract way, on the kinds of uses you want to support. And the things I'll tell you about will be appropriate for some of these things, but not appropriate for others. And now what I will spend a fair amount of time delving into is also, we have to think, what do we mean by protecting privacy? And that's turns out to be a fairly tricky question, but we now have some, at least in some contexts, good answers for what that should mean. Okay, so all right, as a theorist, I don't really work too much with real data sets. So here's a toy medical data set. Has some demographic information, blood type, other attributes you might imagine, maybe some very sensitive information like HIV status. And what's the traditional approach for dealing with privacy in data sets like this, and still quite commonly used, is to just try to anonymize the data set by removing identifying information. Right? You remove name, address, social security number, and so on. And now, looking at the data set, it's not obvious who's who, and maybe you think this data is safe to share. Post on the internet, let anyone do the research they want to do with it. Unfortunately, it's now quite well understood that this is a really problematic approach to protecting privacy. And if you think about it a moment, it's not too hard to see why, that the information that you haven't removed from the data set is often still enough. It doesn't take much of it to uniquely identify people. And it's not hard, once you realize that, to start coming up with examples of how you can actually figure out who's who in a supposedly anonymized data set. So one dramatic example, one of the sort of first ones that got a lot of attention by LaTanya Sweeney in the late 90s, took anonymized medical insurance claims data that was released in the state of Massachusetts, and took some of the fields that remained in that data set, zip code, date of birth, and sex, and realized that these three things that each seem fairly innocuous on their own. A lot of people share the same birth date as me. A lot of people are the same sex as me. A lot of people live in the same zip code as me. Nevertheless, these three characteristics uniquely identify well over 50% of the US population. And by linking this on these fields, this medical data set with publicly available voter registration lists, she was able to identify a lot of the subjects in the data set, in particular that of William Weld, who was the governor of Massachusetts at the time. Okay, so this is just one example. Since then, there have been many more, and ones that are much more subtle. And it's not so easy to think what fields might a potential adversary be able to exploit for figuring out who's who in an anonymized data set. All right, so this traditional anonymization is kind of on its way out as an approach for dealing with privacy. An alternative approach, which will be the focus of the talk and is starting to be used by a number of government agencies, is to not try to release an anonymized version of the data set, but instead, so don't give people direct access to the data, but set up an interface that mediates access to the data. So people interested in analyzing the data set might submit queries, and somehow this interface, it's an algorithm, it's going to be a computer program, will figure out how to answer these queries in a way that's still useful for the data analysts, but protects the privacy of the subjects. Okay, so this is, as I said, we will focus on this approach, and so this is a good avenue to pursue, but it's not as simple as it might seem at first. Okay, so what does it mean to protect the privacy of the subjects? All right, so in particular, we can't allow arbitrary queries. You don't want someone to be able to ask the query, what is Mr. Smith's HIV status? Right? Clearly, that's a query that you shouldn't answer. You don't want it to answer questions like, how many people are female and born on April 3rd, 1971, and so on, are HIV positive, right? Because that effectively is picking out a specific individual in the data set and getting information about them. And then a common approach, so we somehow want to limit ourselves to just aggregate queries that are not about specific individuals. But even that's tricky. So a common thing you might see in survey results is they won't give answers that are too small to try to deal with this issue. But again, it's not hard to come up with examples where you can take two questions where the answers are not too small, right? But the difference between them tells you about a specific individual. Or what now, all right, so we maybe deal with this too, but now what about linear combinations of the answers of more things? All right, so it becomes this cat and mouse game. You try to protect, and then someone will say, no, I can still do something bad with it. All right, I'll patch my system to deal with that attack. Let's come up with another fix, and so on. All right, so what you'd like to get out of this cycle of coming up with a countermeasure and attack, a countermeasure and attack. So as Oded Regev maybe conveyed in his talk yesterday, modern cryptography has managed to get out of this cat and mouse game by being able to give a proof based on widely believed conjectures that no attack is possible. All right, so you're not just playing this game of one attack and one countermeasure, and we'd like to do the same for these privacy problems. All right, so one kind of approach that, again, not thinking about what is the definition yet of privacy, that seems promising is, for a lot of statistical type of queries like the ones we were talking about, if we introduce some noise into the results, then at least that seems to interfere with these kind of linear algebra, linear combinations of results type attacks. That was also the subject, I think, of Oded's talk, right? The noise makes solving linear systems much harder. All right, so this is good, but here too perturbation on its own is not necessarily going to be enough, and kind of one of the first steps of getting out of this cat and mouse game is fortunately or unfortunately, a negative result by Dinur and Nissim that says there's some limitations to what we're going to be able to achieve, no matter how hard we try, no matter how clever we are in designing this interface. So let me describe the result. I'll try not to be too technical in doing so. All right, so let's abstract and assume we have only just Boolean attributes in our data set. N throughout the talk will be the number of people in the data set. D, let's say we have D attributes in the data set that are kind of public information. Think of this as directory information. You know the population that's in the data set. Maybe it's the residents of a particular town. But there's one sensitive attribute that we might be interested in protecting, like HIV status or whether someone likes Broadway musicals, whatever you consider to be sensitive. What they said is, suppose what we release, I want to know the correlations between all of these, say, demographic attributes and the sensitive attribute. Okay, that's the statistical information I want to release. So that's just the dot product between each of the columns and this last column. And I'll divide by n to normalize for the number of people in the data set. But I'm going to introduce some noise to prevent these problems that we talked about, these linear algebra attacks. And the amount of noise that I'm introducing is going to be little o, so vanishing compared to 1 over square root of n. Why is that? Because 1 over square root of n is about the magnitude of sampling error that I'd expect in a data set of size n, and I don't want to introduce more noise than my sampling error. And they said, if we do this, and the number of statistics we release, d here, is bigger than n, the number of people in the data set, then actually this is, no matter how you do it, all right, so I'm not saying I just add plus or minus. No matter how I release these approximations, if my error that I introduce is this small, and I release enough of them, more than n, there's a devastating attack on privacy. And in particular, you can recover almost this entire final column of sensitive attributes, right? All but a vanishing fraction of it. Great. So that's going to be a lot of the subject of the rest of the talk. So great question. So yes, it's essential for this result. All right, so I don't want to get too technical in the proof, but just point out what the kind of idea that goes on in this. It has to turn out to do, so what are we essentially releasing is an approximation to the, what happens if you apply the matrix given by these d columns, right, the transpose of it, to the last column. And what one uses is that if this matrix, say, is random, all right, so I didn't mention, the matrix is random. Let's say each one's just an independent 50-50 coin toss. With high probability, such a matrix is going to have large discrepancy. So on any vector that's far from the true column of sensitive attributes, that's far from it in, say, L1 norm, at least one of the answers is going to be significantly different. All right, and that's what tells you that these approximate answers are going to be enough to reconstruct almost this entire column. Okay, and then the way you can reason about this discrepancy is, for example, through the singular values, the bounds on the singular values of a random matrix. Okay, but that's more important is just this upshot here.
So it's a statement that only holds on if you make assumptions about the public attributes.
Yes.
Because if they're all the same, then I know nothing.
Exactly, exactly. But we don't really need it to be random. All we need is this large discrepancy property. That's right. And so one can even write down explicit matrices with this property also. All right, so the upshot, what they provided was an adversary, an attacker. Not obvious from what I've told you is that actually one can implement it efficiently. They also show how you can give an efficient algorithm to implement the attack using linear programming, such that for any mechanism that releases these approximate correlations between columns and the sensitive attribute that is sufficiently accurate, all right, so this accuracy, I mean really the error in accuracy, with high probability over the data set and the answers provided by the mechanism, this adversary will reconstruct almost this entire last column. Right? And the thing I want to stress here, and how we're getting out, I mean how this is a step towards getting out of the cat and mouse game, is they give a statement that is applying for all mechanisms, all ways of trying to protect the privacy while releasing accurate information. Okay, so it's trying to reason. It's a kind of it's a central way we think in theoretical computer science. Is we're not so much interested in the properties, in many cases, of a particular algorithm, but we're interested in what the reasoning about the space of all possible algorithms for a problem and understanding what the limitations of those might be. Okay, so takeaway message from Dinur Nassim is first, even aggregate statistics, and ones that are not, these were not statistics that were obtained by an adversary deviously making queries about a particular person, but these were just random dot products of attributes with the sensitive information you might release. Even such things can carry subtle privacy risks. And in particular, there are these fundamental limits to how much utility, how much accurate data, statistical information we can provide while protecting privacy. And so what we need is a quantitative theory to help us reason about this trade-off between how much statistical information we can provide and our desire to protect privacy. And we need a quantitative theory that will allow us to really have assurances that we've protected ourselves against all possible attacks like this. Okay, not again on the positive side. We want to reason about all possible attacks the way one does in cryptography. And that's what differential privacy offers. And this came out of a series of papers inspired by this negative result of Dinur Nassim, series of papers about a decade ago. And what differential privacy is it offers first and foremost a definition for what does it mean for a data analysis interface like this to protect privacy. And what it requires is that the effect of each individual in the data set should be hidden from someone interacting with the system from the outside. All right, so let me be more precise about that. So imagine an arbitrary adversary interacting with the system, all right, possibly asking deviously chosen queries to try to pull out information about individuals. And we imagine there's a particular individual in the data set that they are interested in learning information about. It might be someone they already know a lot of information about, like a neighbor or a former employer. And as a mental experiment, we imagine what happens if we take this person's data, remove it from the data set, and possibly replace it with arbitrary other values that have nothing to do with that original person. Okay, and what we require, what differential privacy requires, is that an adversary interacting with the system from the outside should not be able to tell the difference. Okay, so that's the sense in which your privacy is protected. Someone interacting with the system, it's as if they're interacting with the system without your data in it, or replaced with someone else's data. All right, so how could this be achieved? Before getting more precise about the definition, let's see an example to give a feel for how this might be possible. So imagine we ask one of these kind of counting type queries, ask about a fraction of the people in the population that satisfy some property, say have blood type B and are HIV positive. Well, the claim is that we could satisfy this concept of differential privacy as follows. Compute the actual answer and add a small amount of random noise. Okay, why a small amount of random noise and how much random noise? Well, let's think any one individual in the data set can change this actual answer by almost plus or minus 1 over n. Because it's a fraction of people in the population, and one person will change the answer. It contributes only 1 over n. And so intuitively, at least, if we add some random noise of magnitude bigger than 1 over n, we should be able to obscure the effect of each individual. And the point here, okay, is that at least for this simple case of just producing one statistic like this, we are introducing an amount of noise, an amount of error that vanishes as n goes to infinity, and also goes to 0 faster than the sampling error, which we typically expect to be on the order of 1 over square root of n. All right, so now that was just a simple sort of motivating example to keep in mind as we get a little more precise about the definition. All right, so what that example tells us is it's a good idea in defining differential privacy to have this data analysis interface be a randomized algorithm that introduces its own randomness, its own noise into the way it computes statistics so as to protect privacy. And now the definition, what we require is that for any two data sets that differ on one row, okay, so think of your actual data set, regardless of what it is, and take any person's data in that data set and remove it and replace it with arbitrary other values. All right? So any pair of such data sets and any sequence of queries that someone might submit to the interface, the distribution of results that someone sees from the outside should be approximately the same under database D and this neighboring data set D prime. The probability distribution of results. And these probability distributions are taken over the random noise that's injected by the interface. Okay, and this approximately the same is governed by some parameter, epsilon, that's measuring your level of privacy protection. Okay, so I said we're going to give a quantitative theory of privacy protection, and epsilon is the measure here. Yes?
Well, to keep me from asking my second question about somebody else, even though I wanted to know that. Right? I mean, you're saying only one row, all arbitrarily many queries.
All right,
But,
so
I can switch the person for the other query.
right, but so good question. So few things here. All right, so one, in terms of the example, I haven't told you yet how to handle many queries, how to construct a mechanism satisfying this definition. All right, but why should you be happy with a definition like this? All right, so think of my perspective as someone in the data set. Right? What this is saying is that from a potential adversary's point of view, it's as if my data wasn't in the data set. All right? So they may start out by trying to learn something about one person and may switch to trying to learn about someone else. But I'm assured that throughout this process, no matter how they've divided their time among people, what they see is going to be essentially the same, even if my data wasn't there. And so somehow this is not a statement about, from the adversary's point of view, who the adversary is trying to attack. It's kind of, think of it as a statement from the perspective of each individual data subject. Right? Over the totality of queries, each subject should be protected. All right, any other?
What's in this epsilon is if I were to test D versus D primes, I would include random guessing by epsilon.
Yes. So I'll be more precise about it in just a moment. That's right. So, all right. So it turns out to matter for the definition to capture intuitive things we want about privacy protection. It turns out to matter how you measure the closeness of these distributions. And the definition that kind of turns out to behave right, but I won't really get too much into why this particular definition in the talk, is to adopt the multiplicative definition here, right, where the probability distribution, so the probability on any event, any set of possible outcomes, is the same under D and D prime up to a multiplicative factor of say, 1 plus epsilon. Right? Often you'll see e to the epsilon here, but approximately the same. And to Emmanuel's question, one consequence of this is that if you think of it from a Bayesian point of view, this will govern if you think of the posterior belief under database D and under database D prime, they will be the same up to 1 plus epsilon. All right, the other thing that's hiding in here, and for a lot of the results I'll be talking about, so epsilon you should think of as a small constant, okay? That's the level of common thing we think of when we talk about differential privacy. 0.1, maybe 0.01. Okay. In addition, we often allow also a very tiny additive term here, which we think of as being extremely small, like the small probabilities you talk about in cryptography, 2 to the minus 30 or smaller. Okay. But it won't really be apparent in the talk. Just mention it for completeness. All right, so now let me be a little more precise about that example. I said we add noise on the order of 1 over n. Well, once we have have specified our measure of closeness between distributions, it also tells us what's the right distribution to add noise. You can use Gaussian noise. It turns out that better match with the definition, produce more accurate results, is to use this Laplace distribution, a two-sided geometric distribution. And when I said your noise should be a bit bigger than 1 over n, how much bigger should be determined by this measure of privacy protection, epsilon? OK, so that's just for answering one query. But now what if you want to answer many queries of this type? Let's say these kind of fractional counts. What fraction of the population has some property? What fraction of the population has another set of properties? And so on. So it turns out that, and again, supporting this idea that differential privacy is a quantitative theory of privacy protection, that differential privacy has nice compositional properties. And in particular, it's not hard to show that if you execute k differentially private algorithms, or lose k differentially private statistics, the level of privacy protection degrades by at most a factor of k. I mean, that's a fairly straightforward calculation. A little bit less immediate is that actually it turns out that it degrades more slowly than that. And one can show that it degrades only like square root of k, roughly. And all right, this we were talking about these polylog n factors earlier. So that's what this little tilde is hiding here. I'm going to completely ignore them. They matter, of course, in practice. I'm going to ignore them in the talk, and in fact drop these tildes just to not clutter the notation. Good. So what this tells us is that if I want to be able to answer k queries using this basic mechanism, well, one way I can do it is by increasing my noise magnitude by a factor of about square root of k, because that'll improve the privacy protection by about a factor of square root of k, and then I can apply composition. All right, so let's plug in some numbers here. If the number of queries we're asking is smaller than n, or asymptotically smaller than n, then the amount of noise I introduce is asymptotically smaller than 1 over square root of n. And this matches up with the attack we saw at the beginning, the Denurian attack. Right? So we said we can't answer more than n queries with this kind of error, otherwise we're vulnerable to an attack. And what this differential privacy tells us is that actually we can get close to that bound. We can answer nearly n queries with this kind of small error, less than the sampling error. All right, but now what if we want to answer more queries than that? We don't want to have to shut off our system after just n queries are asked if I have a data set of size n. So this tells us that we can go close to n squared queries and still be giving interesting results, where the amount of error we're introducing is vanishing, is arbitrarily small. It's bigger than the sampling error, but at least it's vanishing. It's still interesting information. All right, and so a question is, can we do better than this? All right, or is this the best possible? All right, so I will spend a lot of the next part of the talk talking about that question in more detail. But maybe before doing so, it's worth stepping back and just reflecting a little on the definition of differential privacy, some other interpretations of it. All right, so another maybe useful way, more semantic way to think about differential privacy. It doesn't say that an adversary won't learn anything about you. Okay, because the point of a data set like of data analysis is to learn about the population. Learning things about people in general teaches you things about individuals. Right? But what it does say is that what someone learns about me is not because of my data in the data set. It could have learned from everyone else's data. Right? Because what it learns is essentially the same even if my data is removed. All right, we're already motivated. It's designed to protect individual level information. But I want to give a couple of sort of just caveats. One can misuse differential privacies. One's not aware of these things. So one is that there's no protection for information that's not localized in the data set to, like we need a way of picking out what it's saying, what's one person's data, right, as part of the definition. If there's some information about you that's somehow spread throughout the data set, right? So maybe some embarrassing photo has gone viral and everyone has it on their page and it's in the data set, that's not going to be protected because that's now from the perspective of differential privacy, that's now global information. It's not individual level information. And then also, it's worth pointing out, there's also, just like there's no guarantee that someone won't learn something about you, there's also no guarantee that people won't be harmed as a result. All right? So it's not, someone learns something about the population, they may take some crazy decisions based on that harm lots of people in the data set. Okay? But again, it's not because of your data in the data set that you are harmed. All right. But the last thing I wanted to stress, and again about this getting out of this cat and mouse game, is these interpretations about what differential privacy does protect hold regardless of what auxiliary information an adversary has. Okay, because this indistinguishability between the data set with your data in it and your data set with your data removed is a statistical one that made no modeling assumptions about the adversary's prior information or what strategy the adversary uses to attack the system. We've made no assumptions about that. Okay, and so, right, so when we have a differentially private mechanism, we've given a particular mechanism such that for all adversaries and all databases and every individual in those data sets, the adversary cannot distinguish the mechanism on the data set and the mechanism with, say, the ith person's data removed. Yes?
Give a concrete example. If the adversary knows everything about you except if you're HIV or not, what amount of information in terms of epsilon can he learn from? How does epsilon convert kind of information?
Yeah, so it converts into this relation between, say, posterior beliefs. So think of what the adversary's posterior belief that you're HIV positive if you weren't in the data set. Compare that to the adversary's posterior belief if you are in the data set. And these are going to be the same up to a 1 plus epsilon factor. All right, good. All right, so now let's get back to this question about how many queries can we answer and how accurately with differential privacy? All right, so we've seen that by composition, it suffices if I want to answer k queries on a database of size n. I can introduce noise of magnitude about square root of k divided by n. And we saw this attack of Deneur-Nissim, which is not hard to show that it contradicts differential privacy when you can carry out that attack. Well, we said that you can't introduce noise. Right, when k equals n, you'll be vulnerable to attack if your errors is little o of 1 over square root of n. And this can be generalized to this more general statement here, that you put a minimum of k and n, square root of that divided by n. All right, so the question we asked earlier, when your number of queries is bigger than n, what's the right answer? These match when k is smaller than n, when the minimum of k and n is k. But what about when you want more than n questions? And then another very interesting question is, what about things other than these counting queries, these fractional counts in the data set? Right? That's many of the data analysis you want to do is not at least directly represented in this way. All right, so to the latter question, there's a huge amount of work, really rich literature of algorithm design in differential privacy, showing that in theory, many, if not most, of the kinds of data analysis that people like to do is compatible with differential privacy. The statements are often of the flavor of what I said before, that as n, the size of your population, goes to infinity, the utility, the convergence rates, and so on of your differentially private analyses are similar or essentially the same as the non-private algorithms. There was a great workshop at the Simons Institute in Berkeley a couple of years ago on big data and differential privacy, where people talked about a lot of these other sorts of things. All right, but in this talk, I'm going to focus on these very simple kinds of queries because I'm interested, based on the title of the talk and my kind of background as a complexity theorist, in understanding this border between possible and impossible. And when we're trying to understand limitations, we should first understand the limitations in the most basic kind of statistics, and then try to leverage that to also understand limitations on more complex things. And it's turned out to be the case as well. All right, so one result I want to tell you a little bit about says that when k is bigger than n, this bound that we saw that's achieved by differential privacy, the square root of k over n, is the right answer. Okay, so differential privacy is impossible just beyond that. And now, a critic might say, well, differential privacy is a very strong definition of privacy. And it's not letting us do much useful stuff, so maybe we need a different definition of privacy, right? Or we want to go beyond this limitation. And so the next question is this just something that's an artifact of differential privacy, or is it reflecting an actual vulnerability? And more recent work, we kind of worked a bit harder to actually provide, or this is no longer a mathematically well-defined question. I have realistic in quotes here, but to show that actually this bound is, this limitation can be shown by a fairly realistic kind of attack. All right, this is joint works with Mark Bunn and John Ullman. Mark Bunn, my PhD student. John Ullman, former PhD student. He was a Simons Junior Fellow last year. And this subsequent work with Dwork, Smith, Steinke, and Altman. Okay, right, the border. All right. Yeah, I think I have enough time to tell you some of the ideas here. I'm just going to focus on the case of not the kind of really, to keep things quantitatively simple. Suppose we want to release about n squared of these kind of counting kind of statistics. And actually, the kind of counting statistics I'm going to talk about are just going to be column sums. So you have Boolean data, and I'm just releasing what fraction of the population has the first attribute, what fraction of the population has the second attribute, and so on. Okay? Column means. And just want to say that you can't do anything useful when your number of columns that you're releasing approximate means of is bigger than n squared. And this is going to use a connection between something called fingerprinting codes and differential privacy. This next set of slides on the proof, some cute slides from my student Mark. All right, so what are fingerprinting codes? So these are invented by Dan Bonnet and Shaw 20 years ago for an entirely different problem, or at least what at the time, this is well before differential privacy was introduced. They were looking at the problem of content distribution, digital content distribution, or not necessarily digital, even analog. I want to release something like a movie, but I'm worried that people might pirate it. Okay, so I have this movie, all right, not Star Wars, log Star Wars, because theoretical computer scientists like log star as a function. And the way I'm worried about piracy, so these are the users here. Yeah, I know they're the characters in the movie, but they're also the people receiving the movies. And in order to help catch pirates, I'm not going to give them all exactly the same version of the movie. Right? So for every scene in the movie, I'm going to make 2 slightly different versions, right, that maybe are hard to tell apart, but I can tell them apart. And so I guess Yoda here has the green version in the first 3 scenes and the blue version in the next 2, but it's different for everyone. Okay, and the worry is, right, if someone pirates it, like, well, Yoda makes copies of his movie and sells them to others, well, since everyone has a different version of the movie, you can easily trace and figure out, this is Yoda's movie. He was the pirate, right? But, all right, so that's easy enough. All you need is the different copies of the movies to be distinct. But a more severe problem is, what if few of them get together and collude to do the piracy? Okay, so say Yoda and Luke get together, and now they know that we've done this. They can't tell the green and blue apart, but they know that we've done this kind of trick here of giving different versions of the movies. So on the first scene, they'll use Luke's version. Second one, they'll use either one. This happens to be the same. Third one, they're using Yoda's, and so on. Right? They splice together their copies of the movie. So now we still want to be able to trace. And what fingerprinting codes require is that I'm guaranteed to be able to do so. So if I take any coalition of people who have colluded to produce a pirate version of the movie by splicing their versions together in this way, I will be guaranteed that I can figure out at least one of the users who contributed to this pirated version. And I can't be sure that I can figure out all of them, because they might have just used Luke's scenes throughout, right? Not used any of Yoda's. All right, so now what does this have to do with differential privacy? Well, let's start calling blue and green 0 and 1. All right, so now this is starting to look like a database here. N people, D columns. And all right, so now we have some coalition here. All right, so they have their vectors of 0s and 1s. And this condition here says if they have both ones if they both have 1s in a particular column, then the thing they produce should have a 1. If they have both 0s, then the thing they should produce should have a 0. And otherwise, it could be either, because they're combining their movies in arbitrary ways. All right, so for all coalitions, any coalition here, and any method they use for splicing their movies together, actually even ones that can tell the 0s and 1s but are just restricted to splicing, we should be able to figure out at least one person in the coalition, all right, with very high probability. And this probability is kind of over what the pirate does, but also over we're going to generate this pattern of 0s and 1s in a probabilistic way. And with probability very close to 1, I'll not accuse someone falsely, not accuse someone outside the coalition, and I will accuse someone in the coalition. Yes?
So you take a negation of these problems, namely you just want to identify people who didn't cheat.
Yes.
Allow you to catch two, but you didn't give proof who actually did. Is that just equivalent or?
Proof? I didn't catch the last part.
So you state the problem as you will catch someone. The negation problem is that you can declare all innocent. That doesn't mean that but then you only catch as a group as a one, right? So when you catch one, you have more evidence catching that one than just excluded the innocent people.
I'm not sure I'm following exactly the question.
Why don't you just go on?
Oh, okay, sorry. Maybe offline we can figure out. I'm sorry, I'm not catching. All right. So let's see now. What is the relationship between this and differential privacy? I already gave some hint. Think of this as a data set here. All right, so we say now think of a big coalition. All right, so think of our data set as actually the coalition of pirates that are working together. All right, if they get together and produce this spliced version of their movies, then I will identify at least one person in the coalition with high probability, which means that in particular there must be someone, say Leia, at least one person that I'm identifying with probability at least 1 over n. Right? Because that's the only way I'm going to sum up to possibly get a probability close to 1. On the other hand, if we remove her from the coalition and put someone else in here and someone else's data, then fingerprinting codes also say I shouldn't falsely accuse someone. All right? If I have a coalition without her in it, the probability I accuse her should be very small, much smaller than 1 over n. And this is looking just like what differential privacy protects against. You take one person's data, you replace it with someone else's, and here we're seeing a big difference. In one case, I'm accusing Leia with good probability. In other case, I'm accusing her with very small probability. And differential privacy doesn't allow that. All right, so this is saying, and in a sense that can be made formal, that in some sense fingerprinting codes are the opposite of differential privacy. And this can be formalized, and you really have a dictionary matching up. Think of coalitions as databases. Think of your pirate algorithm as your privacy mechanism. Here, so if we take of accurate answers, so accurate column sums, well, if I round them to 0 and 1 and they're accurate, I will get one of these feasible code words for fingerprinting codes, ones that can be thought of as obtained from splicing. And this tracing algorithm is like the privacy adversary. All right, and so then one can show, or if you have a fingerprinting code for end users with length k, you can't accurately release k attribute means with differential privacy. And then to get our result, we plug in an optimal construction of fingerprinting codes due to Tardish. Okay, so again, we have this dictionary. So an interesting thing here is that what's happened in relating fingerprinting codes and differential privacy is they're opposites, and the good guys have switched roles. This got a little misaligned here, but the adversary in the case of privacy corresponds to the tracing algorithm. It's part of the good guys, the police in the case of fingerprinting codes. And the pirate in the case of fingerprinting codes corresponds to the privacy protection mechanism in the case of differential privacy. All right, so what we really have here is kind of a game, and depending which side can win the game, you either differential privacy is possible or fingerprinting codes exist. All right, and this will depend on the settings of parameters. All right, and so they're kind of strong negations of each other, but actually this quantifier switch is something that you might expect by kind of duality, or those familiar with the min-max theorem in game theory. In many cases, one can justify it. I'll also mention, here we're talking about reasoning about all possible algorithms. In computer science, we often like to reason about computationally efficient algorithms. And in this case, those kind of results actually came earlier, and then kind of it was realized. So they're what are called trader tracing schemes instead of fingerprinting codes due to Chor, Fiat, and Orr, with a connection made to differential privacy in these earlier works. And these allow us to give not impossibility results for differential privacy, but show that certain things are computationally hard to achieve with differential privacy. All right, so I think I have, if I could take just a minute or two to just say, all right, I said that this shows impossibility of differential privacy. What about really showing that there's an attack possible if you try to release so many statistics accurately? And what you need is a fingerprinting code with some kind of the distribution on code books. This matrix should have a kind of natural distribution that you might expect to occur in a real-life data set, a reasonable one. And then you also want that your tracing, which is your privacy adversary, should be able to carry out this telling whether someone's in the data set or not without too much auxiliary information. Right? Because the more information that the attacker needs, maybe the less realistic the attack is. And so we went back, we looked at Tardish's fingerprinting code. So there was some things that were kind of, it actually is a very simple description. The way you generate the matrix, you sample column probabilities, Pj, from some distribution, and then just generate your kind of IID Bernoullis in each column. But there was a very particular distribution that's used there, and one that may or may not expect to come up in practice. But the other, maybe more problematic thing is to carry out the attack, you needed the tracer to know this vector of column probabilities exactly, the population parameters. So we managed to kind of remove both of these things. Basically, for kind of any nice enough distribution on the column probabilities, the attack can be carried out. And we can replace knowledge of the column, the population parameters with just a fresh sample from the population. So you get someone who you know wasn't in the data set, and you get their data. Or you get a few people and take an average of it. And yes, we remove the need for these column probabilities. And I guess what I want to say, why should we think of this at least as an attack we should be worried about? This generalizes an attack that was shown to be possible in principle on genomic data by Homer et al. For the case not of an arbitrary accurate mechanism, but for the case of releasing exact statistics. Okay? And here, like in I think Emmanuel's talk, the data we're worried about are these single nucleotide polymorphisms, the presence of or absence of some particular genetic variant. The data set that you're worried about is a case group, a collection of people that have been diagnosed with a particular disease. And so you really care about protecting against this tracing ability of being able to detect whether someone's in the data set or not. And someone might have a particular person's DNA that they use and kind of compare it to the statistical information that's released and figure out, I have high statistical confidence that you were in the data set, and hence you must have this disease. And this paper of Homer et al. Actually got NIH to take down genetic statistics that were available on the internet. And this says, this kind of generalization says, there's not going to be a way we can fix that by just introducing noise or correlating between these different answers. All right, so I think I'm out of time. I maybe just will mention a few other quick things in survey form. A couple minutes? All right, good. All right, so one thing, I restricted attention to just this case of talking about column means. All right. Of course, the kinds of queries that one might have may not be restricted to such simple things. And in particular, if your dimensionality of your data is bounded, you might have lots of queries that are kind of combining information between different columns, like looking at correlations between pairs or triples of attributes. And then the thing that turns out to matter is not how many questions, but the dimensionality of the data. And first, there's beautiful positive results, starting with Blum, Liggett, and Roth, that say if your dimensionality is bounded, you can answer many, many more than n squared questions. All right? Your dependence on the number of questions drops from being square root of k to being logarithmic in the number of questions. You can answer even an exponential number of questions with these strong protections of differential privacy. All right? But there's some price depending on the dimensionality. And we can use these fingerprinting codes also to show that this dependence on the dimensionality is necessary here. Another kind of very interesting place where there's lots of open problems has to do with computation time. So these amazing algorithms that allow you to answer an exponential number of queries with differential privacy have exponential computation time. To answer each question, you compute for time that's exponential in the dimensionality of the data. And in general, one can use the similar kind of connection, but the computational version using these traitor tracing schemes that I mentioned can show that for arbitrary queries, this kind of computation is going to be necessary. But for specific families of queries that you might be interested in, like correlations between 2, 3 attributes, and so on, there are many open questions, and one can do much better than these worst-case bounds. And on the positive side, it's using very beautiful techniques relating to convex geometry, things like the Gaussian width of the polytope a polytope that's related to the set of queries, these discrepancy ideas that I mentioned earlier. But this is a landscape with lots of open research questions. All right, so I guess I will just wrap up here. To conclude, we're starting to get to the point where we are starting to get a kind of a tight understanding of the limits of what can be achieved with differential privacy for basic statistics. And one message that's coming out is that the cost that we're paying for differential privacy, at least in theory and at least asymptotically, is really necessary to avoid attacks that we might be worried about. But as we talk about more complex statistics, there are lots of interesting open problems. I emphasize this idea that kind of pervades differential privacy research of kind of trying to reason about the space of all possible algorithms and all possible attacks. And one other thing that I didn't get to talk about at all in the talk is actually it's turned out that differential privacy has connections with many other really interesting mathematical topics, even ones that have on the surface nothing to do with privacy. And in particular, there's some recent results showing a beautiful connection between differential privacy and protecting against false discovery, the kind of thing that Emmanuel Candice was talking about in his talk yesterday. And in particular, the case where the analysis is done adaptively. All right, I carry out one analysis, and based on the result of that, I decide what's the next analysis I'm going to do. And some of the methods that we heard about don't address because they have this independence assumption between the p-values. And it turns out that differential privacy allows you to protect against these. And also the limitations on differential privacy and the ideas using fingerprinting codes also translate to limitations on how you can protect against false discovery. So regardless of whether you care about privacy, there may be something interesting to look at in differential privacy. And of course, I didn't talk at all. There's a lot of challenges still in bringing, this is all theoretical stuff, talking asymptotically what you can do with differential privacy. A lot of challenges in bringing it to practice, but many efforts happening around the country, around the world in trying to do that. We have some work at Harvard as well along those lines, but I should stop here.